Okay, so a couple of things we're making up. Yet another snow day for snow that will more than likely not occur. But we're going to kind of continue what we started going over on Friday last week before your exam on Monday. And there are several things in the section that we're going over that I actually want to do in person, and I figure you signed up for an in-person class, so I should do my best to do that. All that to say, this video actually won't be all that long. We're going to cover one or two things that are important that we'll use throughout the rest of the semester, but then there's other more technical algebraic stuff we want to go over, and I think that'll be better served to be done in person rather than through a video. So this won't be all that long to cover what we would have gone over today. But last week we essentially said, suppose I have something like, we'll go with the two-variable function, f of xy equals x squared y plus 2x plus 3y. And then we said we can get partials of that, partial of f with respect to x. I just treat y like a constant, so then I get, let's see, that's quadratic, so I get 2x and then the y just sits there. Partial of 2x with respect to x is 2. With respect to x, 3y is a constant, so the derivative is 0, so that just goes away. And then by the same token, I can do the partial with respect to y. With respect to y, that's linear, so I'm just left with the coefficient x squared. With respect to y, 2x is constant, so it goes away. With respect to y, that's linear, and I get 3. And then I get those partials. And we finished last week by saying, hey, if I can get these partial derivatives, the partial derivatives are functions themselves, they should be differentiable. Can I take derivatives of those, just like we did in Calc 1, and essentially do higher order partial derivatives? And just kind of a notational thing here, like we mentioned last week, when you do higher order derivatives in Calc 1, you can either use the prime notation, like f prime of x, and then if you wanted to do a higher derivative, you would do f double prime of x, or you can do higher order derivatives, and you maybe get d squared f of dx squared for my second derivative. I could do d cubed f dx cubed. If you wanted to do it with respect to y, you could do d squared y dx squared, etc., etc. There's a similar approach here if I want to do my partials, where say, we're going to keep using that one right there. But say I have my partial, the partial of f with respect to x. If I then want to take the partial with respect to x again, I can do the partial with respect to x of the partial of f with respect to x. And using the same idea that you used back here, if you remember it in Calc 1, this just becomes the second partial of f with respect to x, and we kind of write it using that square notation. I could do the exact same thing for y, but there's one difference here when we do the partials, where here, my variable is always x. But here, since I have multiple variables and multiple partials, then in theory, maybe I want to take the partial with respect to y, and then take the partial with respect to x. And we will go into further detail as to why we might want to actually do that. I'm not going to do it here. But for right now, algebraically, that's a function. I take the partials with respect to x or y. Those are functions, so I can logically take the partials of those with respect to x or y. And again, algebraically, that should definitely work. We can think more about the geometric interpretations of it later this week on Friday, assuming we have school, which hopefully we will. But otherwise, I'll have to make a lot of videos. But algebraically, the idea should still work. And if we kind of use this Leibniz notation, it can occasionally get confusing, so we want to be clear on this. So say, like I said, we start with the partial of f with respect to x, then say I want to take the partial of that with respect to y. So I get the partial with respect to y of the partial of f with respect to x, which I can then write as the second partial of f, but now I get with respect to y with respect to x. But I can also say start with the partial of f with respect to y, like we did there, and then take the partial of that with respect to x. And then I get the second partial of f with respect to, I put my y here, this should be a y. Partial with respect to x, and then y. And just a point here on the notation, here I have the second partial of f with respect to y with respect to x, but in this notation, we're thinking about this as a composition, which means even though this is partial of y, partial of x, I do the x first, then the y. Here, this is partial of x, partial of y, but I do the y first. We do it in reverse because this is kind of a composition notation here. But, the way to make this even more fun, in Calc 1, you have this Leibniz notation, you also have the prime notation, and we mentioned in class, we can't use that prime notation anymore because we just don't, I'm out of things to put as superscripts. But we said you can use a subscript notation where, say, I can have the partial of f with respect to x, and we just write f sub x. If I wanted the partial of f with respect to y, that would be f sub y. If I then wanted to continue that and say, take the second partial of f with respect to x twice, that's just fxx. If I wanted the second partial of f with respect to y twice, that's f sub yy. And you just kind of take the partials as you go. But if I wanted to do something like this, say I wanted to do this one, I wanted to do the second partial of f with respect to x and y, but I'm doing the x first and then the y. In the Leibniz notation, I write it this way, backwards because of the composition. When I write it in subscript notation, you do them forwards. This is a partial with respect to x, that's with respect to x, and then with respect to x. So this will be f sub xy, but in Leibniz it's yx. So just make sure you keep that straight. As I've said before in class, I'm going to deliberately go back and forth between all the different notations just to get you used to all of them, because you never know what future classes and textbooks and YouTube videos and whatever, what notation they'll use, and you have to get used to all of them. As a student, I actually preferred this because it was straightforward and direct. You could just read your partials left to right, which seemed logical in my head. As an instructor now, I actually prefer that because one, like I said in class, it's just cool to write the partial notation. And two, because I actually like this idea right here, and like I've said in class, there's some algebraic ideas that you can get out of this that we'll use for some of the stuff we're going to go into. So we're ultimately going to use both of them. And like right here, if I wanted to do the second partial of f dx dy, I'm doing the partial with respect to y first and then x, so that would be fyx. So again, just make sure you keep all this notation clear and you know which partials you're taking and in which order. But out of this, we get a definition, and we have what's called continuously differentiable. And I want to write the definition more or less word for word out of your book, just so we're clear on it. Let f be defined on an open set O if its first partial derivatives exist and are continuous on O, then f is continuously differentiable on O. So say those over there. I have this function, I take its partial with respect to x and with respect to y. So its first partial derivatives exist and are continuous, those are clearly continuous. Then f is continuously differentiable on O. But I can also kind of continue that for all my higher partials. So I'm not going to rewrite the whole definition, but essentially, if second partials exist and are continuous on O, then F is continuously twice differentiable on O. And you could continue from there. But we understand that ultimately my goal is to redo everything we did in Calc 1 and Calc 2 just for multivariable functions. And one of the things we haven't done yet is to take a function, in this case a multivariable function, and then say find maxes and mins and things like that. And if we remember Calc 1, in Calc 1, in order to find maxes and mins and concavity and stuff like that, we use the first derivative and the second derivative. We had a first derivative test and a second derivative test. And the question is, does that work here? Now I have a surface in space. Finding maximums and minimums still seems like an important thing. So I'd like to see if there's something similar to the first and second derivative tests for single variable functions that will work for multivariable functions. And this is kind of the start of that, where instead of just taking the first derivative and the second derivative, well, now I have directional derivatives, but now I have these special cases of directional derivatives, my partials, and I know I can take higher order partials, so maybe I can come up with a second derivative test that instead of using the second derivative, uses second partial derivatives. And that's kind of what this is leading to right here, where in Calc 1, you just needed your function to be continuous and differentiable. That's kind of what we have here. I want my function to be continuously differentiable, meaning the partials exist and are continuous. And since I kind of understand that ultimately I want to come up with a second derivative test, what we're really going to look for is functions that are continuously twice differentiable, meaning their first and their second partials exist and are continuous. So just kind of keep that in mind. There's a reason for this. The one thing I would point out, and I've kind of mentioned it before, and it probably comes up in a lot of your math classes, are there functions that are not continuously twice differentiable? Yes. But frankly, they're really messed up functions that we're not actually going to deal with, because the purposes of this class are to deal with multivariable functions where we can actually do the calculus on them, which means they'll be continuously twice differentiable. So all the kind of regular functions that we're used to will be continuously twice differentiable, but from a math perspective, it actually is important to check to make sure this condition holds. But because of the way the class is structured, it will always hold for what we're looking at. But I do point out there absolutely are functions that are not continuously twice differentiable. I'm pretty sure your book mentions at least one, or Google is your friend. But if we look over there, clearly that function is continuously differentiable because I took the partials and they're continuous, and they exist and they're continuous, so I'm good. What if I wanted to take second partials? So just to run through this really quickly, if I take my second partial of f with respect to x, that's the first partial with respect to x. Take the partial with respect to x again. X is linear, so I get 2y, so that checks out. 2 is a constant, so it goes away. I can take my second partial of f with respect to y. There's actually no y's here, so that's 0. So that exists, it's 0, so we're good there. But then what if I wanted to kind of do the other thing where I do it with respect to x and then y, or y and then x? And in mathy speak, those are called mixed partials. So say I did the second partial of f with respect to x and y. Here I do x first and then y. So there's my partial with respect to x. If I take the partial of that with respect to y, y is linear, so I get 2x. 2 is constant, so it goes away. Then if I do the other mixed partial, the partial of f xy, so with respect to y first and then x, with respect to y first, then I take the partial with respect to x. With respect to x, derivative of x squared is 2x. That's a constant, and it goes away. And I will also point out, we're doing this for 2 variable functions. I could also have my partials for 3 variable functions, and then you get a whole bunch of mixed partials. All the ideas would work the exact same. We're just doing this for 2 variable ones. But then one thing we immediately see is, one, all the second partials don't exist, even if there's 0. They're continuous. So this is clearly continuously twice differentiable. But then if I look at my mixed partials right here, if I do the partial with respect to x and then y, or the partial with respect to y and then x, I get the exact same derivative. And then from that perspective, you say, is that always true? Will it always happen that it doesn't matter the order of the mixed partials? Will they always end up being the same? So then in theory, I don't have to do both of these. I can just pick one, and that'll be my answer for both of them. And it's a little bit beyond this class, but for as far as it goes, as it turns out, that will always be true if your function is continuously twice differentiable. Which again means there are functions that are not continuously twice differentiable, so there will absolutely be times when it's not true, but for the purposes of our class, it always will be true, which means all of our functions are continuously twice differentiable, so all of the mixed partials will always be equal. That's actually a theorem, and let's see if I spelled the names right. It's either Arrow's theorem or Schwarz's, but there's no T, so it's Schwarz's theorem. It's named after both of these people. That's clearly Schwarz. That's clearly French. So I'm gonna assume it's probably Clairaut. I actually thought it was Clairou, but I was spelling it wrong. I think A-U-T is O, so I think it's Clairaut's theorem, but you know, Google Translate, have them translate it for you. But essentially, the theorem gets 2 names, but all it says is mixed partials are equal. And I do stress, this is absolutely fundamentally important. A lot of the algebra that we do throughout the rest of the semester, and a lot of the theorems that we come up with, will be based off of the fact that I can take all of these mixed partials and dy dx and dx dy end up being the exact same thing. And again, that would expand to dy dz and dz dy, depending on what your variables are and all of that. But this little idea is fundamentally important. Like I said at the beginning of this, several things in this section are fundamentally important. Some of them are really algebraic in nature, and I wanted to save them for in class so I could answer questions as we went through them to make sure everybody's understanding it. This is really important. We'll use it a lot, but we'll use it so often that it'll pretty much become second nature, which is why I'm okay just doing this by way of video. But I'm gonna post this video for you to watch online, and then I'm gonna post a bunch of homework. Basically, we now have regular directional derivatives. We have the limit definition as h approaches 0 for the directional derivative, and then we have these special cases of the directional derivatives, the partial derivatives. And by extension, we have higher partial derivatives. You're just gonna mess around doing all of those, and I do stress, just so we're clear, and you've taken 2 exams at this point, so you know I'm not trying to trick you here, just like in Calc 1, you absolutely need to be able to take derivatives by way of the definition, which means you need to be able to take directional derivatives by way of the definition of the directional derivative. We're actually going to do something similar to that in class on Friday. That's the really technical algebraic stuff I was mentioning that can cause confusion, which is why I want to do it in person. But you absolutely need to be able to do it. You're going to do some for the lab I'm going to give you in post. And then you need to be able to take these higher partials using all your derivative rules, just like you did in Calc 1. And hopefully we have class on Friday, because yeah, it's not snowing yet, as it is.